Now there is a simple concept of electric dipole, and it is a very important concept. Why is it so? Because in nature there are so many molecules and material which although may be electrically neutral, that is having both positive and negative charges in equal number or equal quantity, but if they are placed in some external electric field, so what will happen? Let us say this material is having positive negative positive negative charges, equal charges intermingle with each other. But if I put it in an electric field, what will happen? Positive charge will move towards the field and negative charge will move away or the opposite direction of the field. So there is this separation of the charges now. Similarly, there can be some molecules which have permanent separation, like H2O molecules. So this kind of scenario can occur in so many materials. So we come across the phenomena of dipoles. So dipole is nothing simply when two opposite charges are separated by a small distance d, minus q to q, let us say. So this quantity minus q to q is called the electric dipole. Now we need to find the electric field or potential due to this electric dipole because it is so frequently occurring in nature. So we should know about it. This is an important quantity. So we will try to derive the electric potential due to this dipole by a very ingenious method or simple method by using the concept of differential or the gradient. And this we have already seen in our previous one of the lectures, the similar concept. So let us see how to do it. Let us say this is z-axis, this is point charge q placed at origin, and this is point p which is at r. Okay. So potential at P due to this charge Q will be 1 by 4 pi epsilon Q by R. Okay. Now what will happen if I move this charge by delta Z? So let us say this charge is now at here. So this, let us say, is R dash. So phi P, let us say I will represent it as phi dash. P will be 1 by 4 pi epsilon naught Q by R dash. Now this change from phi P to phi dash P is similar to the change if I do not move this charge to here. Instead I move this observation point or the field point by the same distance delta Z. Let us say now at this point we have to find, and charge is still here. So it is parallelogram. So this will be again R dash. So at this point P dash, potential will be again 1 by 4 pi epsilon naught Q by R dash. So you see that the effect of moving a charge by delta Z along the Z axis is same as if we have moved the observing point by minus delta Z, means in the opposite direction of positive Z. Okay. So this is the same effect. Now we can use that this delta phi at point P is approximately equal to dou by dou Z, because in the Z direction we are seeing of the potential, and since the movement is in minus z direction, so minus sign will be like this. And why we are having approximate sign? Because we are considering that this is some finite movement. If this limit tends to 0, then this sign will change to equal. Okay, so you see the change in potential is simply minus dou by dou z of phi into delta z, or what we can write as phi 2 minus phi 1 is equal to minus dou by z of phi delta z. Now we will further improve upon it or explain it so that we can find a very closed form solution or the equation for the potential of this dipole. So now in this slide continuing, we can see that what has happened, that we have moved this positive charge by delta z at this point, plus q charge I have moved here. So I can write the potential at point P due to this charge movement as, let us say this is just plus charge we have seen, is equal to simply the potential earlier, which was 1 by 4 pi epsilon naught q by r, plus the change. The change is minus dou by dou z of phi into delta z. Okay, because we know that delta phi is simply phi 2 minus phi 1, or phi can be simply written as phi 2, it implies phi 2 is simply phi 1 plus delta phi. So delta phi is this one, and this was phi 1, and this is phi 2. Similarly, if this charge was minus q, so we could have written phi due to minus charge as 1 by 4 pi epsilon naught minus q by r minus dou by dou z, and let us say this minus q charge was moved by again minus delta z like this. So it would have been plus phi delta z. Now let us say delta z is equal to d by 2. So the total potential at this point due to this plus q charge and minus q charge, which are totally d distance away, is simply phi is equal to phi plus phi minus. So by adding this equation 1 and this equation 2, I could have clearly written using this thing. So this was this thing will get cancelled out, and this phi I will put the value minus dou by dou z of 1 by 4 pi epsilon naught q by r delta z plus dou by dou z of 1 by 4 by epsilon naught minus q by r delta z. So you see it is equal to minus twice of dou by dou z of 1 by 4 pi epsilon naught q by r delta z, and delta z is d by 2. So this 2 is get cancelled out. So in the next slide I can write the potential at point P due to the dipole is phi is equal to minus dou by dou z of 1 by 4 pi epsilon naught q by r d. Now you can see from this thing that this d, if I show in this direction from minus charge to plus charge. So what I will have, and this R, uh, since displacement was in this z direction only, so this R was also in the z direction, so I can write this whole thing as QD. Now this is in the z direction, minus charge or plus charge, dot dou y dou z of 1 by 4 pi epsilon naught R, or we can write it as P dot 1 by 4 pi epsilon I will bring out from this thing, and this dou by dou z can be replaced by the gradient 1 by R. So you see that the potential due to dipole at a point P, which is at distance R from the center of the dipole, is simply minus sign I have forgotten, minus 1 by 4 pi epsilon naught P dot del 1 by R. So this is the expression which we have derived by a very ingenious explanation, and this is a very quite accurate expression and independent of any coordinate system, because it is just using dot product of two vectors. So clearly we can use it anywhere. Now there is one more thing. If I define phi naught as the potential when the charge is 1 unit charge, so it is 1 by 4 pi epsilon naught R. So we can clearly see that phi is simply due to a dipole is simply minus del 1 by R dot Q D, and Q is 1 here now, is simply minus P dot del of phi naught, because phi naught is this. So del of phi naught is simply 1 by 4 pi epsilon naught del of 1 by R. So instead of remembering this full equation, we can remember this equation, that the potential due to dipole is simply minus P dot gradient of phi naught, where phi naught is simply the potential due to a unit charge at the origin. So this is one big result or good result which we can use anywhere, and we have derived it without using any trigonometry, which we have studied in our 12th classes. Now in this next slide, we will solve a numerical example where we can use the similar superposition principle which we have just used in the derivation of the potential of electrical dipole. So this concept is very useful, and let us see its application also. Let us say we are given two spheres, sphere 1 and sphere 2, with charge density rho minus rho, and let us say these two charge spheres are overlapping each other, let us say like this. Since the charge density is same and equal and opposite, so this intersection is devoid of any charge density. This is minus rho and this is plus rho. This is origin of center of this one. So let us say we want to find the field at any point inside this overlap region. So let us say this is point P where we want to find this field. So field at this point will be because of the positive charge sphere and the negative charge sphere. Okay. Now first we will find the field inside a charged sphere, uniformly charged sphere. So let us say this is a uniformly charged sphere. So using Gauss law, that I will take a surface inside this of radius r, and this is total r. Okay, so the total charge will be inside this Gaussian surface will be 4 by 3 pi r cube and E into 4 pi r square. It will get cancelled out, r cancelled out. So E is simply rho r by 3. So inside a charged sphere, uniformly charged sphere with uniform charge density, this is the expression for the electric field. So at point P, since it is inside a uniformly charged sphere, I can write the total field at point P is because of the field due to positive and the field due to negative, and it is simply rho by 3, and let us say this is vector r plus and this is vector r minus, r plus and plus minus rho r minus by 3. So it is equal to rho by 3 r plus minus r minus. Now this r plus and r minus, let us say this is vector L. So you see vector L plus vector r minus is equal to r plus. So it implies r plus minus r minus is equal to vector L. So you see the field inside the cavity is now simply rho by 3 L. Now this L is a constant vector because it is just a vector between these two centers. So you see inside the cavity the field is constant. So this is a good result which we now will utilize in the next slide, in the next question. Now if somehow we are given a surface charge or a charge density such that it is I'm trying to make a spherical surface. Let us say the surface is having a charge density sigma naught cos theta, where theta is measured with respect to vertical. So this line is like this. This is theta. Okay. So you see, because of this expression, the charge density will look like this on this spherical surface, like this. This is the center. So maximum will be here and minimum 0 will be here. Maximum and 0. So maximum charge plus will be here and 0. Again similarly in the opposite direction, minus negative will be maximum here, minus negative, and it will be 0 on this axis. So this is how it will appear. Now it can be proved that this kind of surface charge density can be shown as composed because of the superposition of two spheres with a surface with a volume charge density having let us say rho and rho minus, but their centers are small little bit displaced. So if this is first center, this is second center, these are two displaced, so we will have this kind of distribution. Okay, so this will be similar to the distribution which we have here. So using our experience from the last example, we can clearly see that this whole scenario can be explained like just by overlap of two charge spheres, sphere 1 and sphere 2 with this thing. So this is theta angle Let us say this is theta, and this is plus, and this is minus. Okay, and let us say this is z direction. So now we know that field can be simply written as rho by 3 epsilon naught L, where L is the vector joining plus and minus charge. So the center of plus charge is this, center of minus charge is this. So L is in this direction. So it is simply rho L by 3 epsilon naught minus AZ, if this is the Z direction, Z axis direction. Okay. Now we have to find just the relation between this rho and this sigma is equal to sigma naught cos theta. How to do that? Now you see that this thickness, the maximum thickness, how much it is, or this thickness, not the maximum which we see, what will be the value? Let us see. The thickness will be r plus cos theta at any point minus r minus cos theta, which is simply r plus minus r minus cos theta or equal to L cos theta. So you see that this surface charge is in this thickness only, which is given by L cos theta. So to find the equivalent surface charge density, I can clearly write that sigma is simply rho into the thickness, or equal to sigma naught cos theta, where sigma naught is equal to rho L. So you see the field is simply minus sigma naught by 3 epsilon naught AZ. So here again we have used the principle of superposition of two different charge distributions in finding the electric field. Similarly, we could have find the electrostatic potential also. So in this way we could solve various kinds of numerical examples also. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. And we have created a Telegram group whose link is given in the description of this video, and please join that. Thank you.